Conductors. The substances which allow the passage of electricity through them are called conductors. The conductors can be classified into two categories: metallic conductors and electrolytes. Metallic conductors. Those metallic substances which allow the passage of electricity through them without undergoing any chemical change. The conduction through metals is due to the movement of electrons in the metallic crystals, for example, copper and silver. Electrolytes. Those substances which allow the passage of electricity through their aqueous solutions and also undergo chemical decomposition at the same time. The conduction through the electrolytes is due to the movement of ions produced by the electrolytes in their aqueous solutions, for example, acid and base. Classification of electrolytes. Depending upon the extent of ionization, electrolytes are classified into two categories: strong electrolytes and weak electrolytes. Strong electrolytes. These are almost completely ionized in their aqueous solutions, for example, HCl, NaOH, and KCl. Weak electrolytes. They ionize in aqueous solutions to the smaller extent and have low degree of ionization. Their aqueous solution contains ions in equilibrium with undissociated molecules. The degree of ionization of weak electrolytes increases with dilution and approaches unity at infinite dilution. For example, NH4OH and CH3COOH. Factors affecting electrolytic conduction. Electrical conductivity of the solutions of electrolytes depends on the following factors. The inter-ionic attraction. These are the attractive interactions between the ions of the electrolyte in solution. Larger the inter-ionic attraction, lesser is the freedom of movement, and smaller will be the electrical conductivity. The solvation of ions. These are the attractive interactions between the ions of the electrolyte and molecules of the solvent. Larger the solute-solvent interactions, greater is the extent of solvation and lower will be the electrical conductivity of the solution. Viscosity of solvent. This factor depends upon the attractive interactions between the solvent molecules. Larger the solvent-solvent interactions, larger will be the viscosity and lower will be the electrical conductivity. Temperature. As the temperature of electrolyte solution is increased, kinetic energy of the ions increases. This results in the increase of electrical conductance of electrolytic solutions. Electrical resistance. Every conducting material offers some obstruction to the flow of electricity, which is called resistance. Ohm's law. It states that the potential difference across the conductor is directly proportional to the current flowing through it. V is equal to IR, or V upon I is equal to R. The ratio of potential difference across the conductor to the current flowing through it is constant and is called resistance of the conductor. Its unit is ohm. Resistivity. It is defined as the resistance offered by the conductor of 1 centimeter length with area of cross-section equal to 1 centimeter square. Resistance of any conductor is directly proportional to the length of the conductor and inversely proportional to its area of cross-section. R is equal to rho L upon A, where rho is known as specific resistance or resistivity. Electrical conductance. Conductance is a measure of the ease with which current flows through the conductor. It is defined as the reciprocal of resistance. It is denoted by G. G is equal to 1 upon R. The unit of conductance is mho. Conductivity. It is the reciprocal of resistivity. It can be defined as the conductance of 1 centimeter cube of the conductor. It is denoted by kappa. K is equal to L upon Ra. The unit of conductivity is mho centimeter inverse. Molar conductivity of the electrolytic solutions. Molar conductivity is defined as the conductance of a solution containing 1 gram molecule or 1 mole of electrolyte such that the entire solution is placed between two electrodes 1 centimeter apart. It is denoted by the symbol lambda m. For V centimeter cube of the solution containing 1 mole of electrolyte be placed between two large electrodes 1 centimeter apart, the relationship between conductivity and molar conductivity is given by lambda m is equal to product of kappa and volume. Example on molar conductivity. Let's take an example of molar conductivity. The electrical resistance of a column of 0.05 mole per liter NaOH solution of diameter 1 centimeter and length 50 centimeter is 5.5 into 10 raised to the power 3 ohm. Calculate its resistivity, conductivity and molar conductivity. Let's see the solution. Here given values are R is equal to 5.5 into 10 raised to the power 3 ohm, C is equal to 0.05 mole per liter, R is equal to 0.5 centimeter, L is equal to 50 centimeter. We know that area is equal to pi r square. By putting the values, we get area is equal to 0.785 centimeter square. We know that R is equal to rho L upon A. By putting the values, we get resistivity is equal to 87.135 ohm centimeter. We know that conductivity is reciprocal of resistivity. By putting the values, we get conductivity is equal to 0.01148 Siemens centimeter inverse. We know that molar conductivity is equal to kappa multiplied by 1000 divided by C. By putting the values, we get molar conductivity is equal to 229.6 Siemens centimeter square mole inverse. Measurement of electrical conductivity. The resistance of the electrolytic solution is measured with the help of Wheatstone bridge method. The conductivity cell containing solution of electrolyte is made one arm of the Wheatstone bridge. An alternating current of frequency range 1500 to 3000 cycles per second is applied. Direct current is not used here because it causes electrolysis and results in the change in concentration of electrolytic solution near the electrodes, resulting in polarization effects. The resistances R1, R3 and R4 are so adjusted that a null point is obtained. The null point is indicated by the detector P. At null point, R1 upon R2 is equal to R3 upon R4. R2 is the resistance of electrolytic solution. R2 is equal to R1 multiplied by R4 divided by R3. Knowing the values of R1, R3, R4, the resistance of the electrolytic solution R2 is calculated. The reciprocal of R2 gives the conductance of the solution. Cell constant. Cell constant is equal to conductivity upon conductance. It is represented by G asterisk. It is expressed in the unit centimeter inverse. It is more convenient to obtain the value of cell constant by measuring the conductance of a standard solution whose conductivity is known. For this purpose, a standard solution of KCl is used, whose conductivity is known at different concentrations and temperatures. Cell constant is equal to 0.012886 upon X. Once the cell constant is known, the conductivity can be calculated from the measured conductance or measured resistance of the electrolytic solution. Variation of conductivity and molar conductivity with concentration. Variation of conductivity with concentration. Conductivity refers to conductance of 1 cm³ of the electrolyte. With the increase in dilution, the number of ions present in 1 cm³ of the solution decreases. Conductivity of the electrolytic solution also decreases as the dilution increases. Variation of molar conductivity with concentration. Lambda m values of strong electrolytes are larger than those of weak electrolytes for the same concentration. Molar conductivity of electrolytes increases with dilution. Relative increase in the value of lambda m for strong electrolyte is quite small as compared to that for weak electrolytes. Graphical representation of molar conductivity with concentration. KCl is a strong electrolyte and CH3COOH is a weak electrolyte. A graphical representation shows the variation of molar conductivity with concentration. In case of strong electrolytes, when the concentration approaches zero, the molar conductivity attains a definite value known as limiting molar conductivity. It is denoted by lambda naught m. In the case of weak electrolytes, such as acetic acid, there is no indication that the limiting value can be attained, because when concentration approaches zero, the graph becomes almost parallel to the y-axis. Kohlraus Law. Kohlraus Law states that at infinite dilution, when the dissociation of electrolyte is complete, each ion makes a definite contribution towards the molar conductivity of electrolyte, irrespective of the nature of the other ion with which it is associated. The molar conductivity of an electrolyte at infinite dilution can be expressed as the sum of the contributions from the individual ions. Let us assume lambda naught positive and lambda naught negative represent the limiting molar conductivities of cation and anion respectively. The limiting molar conductivity of electrolyte at infinite dilution is given by V positive lambda naught positive plus V negative lambda naught negative, where V positive and V negative represent the number of positive and negative ions furnished by each formula unit. Application of Kohlraus Law. Some important applications of Kohlraus Law are in calculation of limiting molar conductivities of weak electrolytes, calculation of degree of dissociation of weak electrolytes, calculation of dissociation constant of weak electrolyte, determining the solubility of sparingly soluble salts, and calculation of ionic product of water. Did you know? If the two vessels are entirely disconnected without a salt bridge, then the cation and anion quickly reaches equilibrium and no electrical current can flow. In 1800, William Nicholson and Johann Wilhelm Ritter succeeded in decomposing water into hydrogen and oxygen by electrolysis. Changes in the stoichiometric coefficients of a balanced cell equation will not change E0 value because the standard electrode potential is an intensive property. Kohlraus, who investigated the conductive properties of electrolytes, also investigated elasticity, thermoelasticity, and thermal conduction. Summary. Let us summarize what we have learnt. The branch of chemistry which deals with the study of relationship between electrical energy and chemical energy and interconversion of one form of energy into another is called electrochemistry. A device in which chemical energy is converted into electrical energy is called an electrochemical cell, or a galvanic cell, or a voltaic cell. The electrode at which oxidation takes place is called anode, and that electrode at which reduction takes place is called cathode. Salt bridge allows the flow of current by completing the circuit. It allows the flow of ions but does not allow the flow of solutions. The electrical potential differences set up between the metal and its ions in the solution is called electrode potential. Molar conductivity is defined as the conductance of a solution containing 1 gram molecule or 1 mole of electrolyte such that the entire solution is placed between 2 electrodes 1 centimeter apart. Kohlraus law states that at infinite dilution, when the dissociation of electrolyte is complete, each ion makes a definite contribution towards the molar conductivity of electrolyte.